about strong distortion and transformation groups. Thank you.
Thank you. Thanks very much for the invitation to speak and for the conference generally. It's been great. I want to start with by stating an old question. So this is a question of Schreier of Schreier-Ulam from around 1935. And he asks, does there exist a group? Is there an uncountable group G with the property and let me give this property some kind of a name because I'll refer to it later. I'll call it star. Is there an uncountable group G with the property that for every sequence of elements this sequence is generated by a finite set. So there exists some finite subset of G so that each Gn is in the subgroup generated by S. That's his question. And you notice if G was countable, this condition is equivalent to being finitely generated. So it's really an interesting question for uncountable groups. And he concludes this by suggesting, as candidates or as things to look at, the group of permutations of an infinite set and the group of homeomorphisms of the line. And as a non-example, I mean, if you think of your sort of familiar uncountable groups, say, I don't know, the real numbers as an additive group, this condition is definitely not satisfied. Take a sequence of numbers that are, I don't know, algebraically independent. That can't possibly be finitely generated. And you can generalize that to matrix groups and similar things. Okay. So I don't know Schreier's motivation. I have a guess of what it might be. This is asking kind of a relative version of the embedding theorem of Higman, Neumann, and Neumann. It says that any countable group embeds into a finitely generated group, right? In fact, they can do two generated. This is asking, within a large group, does any, say, countable subgroup embed in a finitely, is it already inside a finitely generated subgroup? That's not my motivation so much. I'm particularly interested in this question because of, yeah.
That's exactly the same year. Of Cermax.
Ah. Okay, I didn't know those were the same year. Yeah, so this is, either one influenced the other or it was in the air generally. Yeah, so I'm kind of interested in this because of some related properties. Of perhaps more dynamical interest. By the way, this is no longer an open question, but I'll make you wait 1 second before explaining all of it. What are these related properties? Here's one. Instead of star, I'll take a property that's a strengthening of it. So one way you could strengthen this is to bound the size of your finite set and perhaps bound the word length of the Gn. Okay, so this property I'll call strong distortion. Okay. And it says the group has a property that for all, So there is a bound, some integer, and there's a sequence bounding the word length. Such that for any sequence of elements in your group, there is a finite subset, but now of cardinality at most m, such that, well, first it generates as above, and the word length of the nth element of your sequence in this generating set is at most Wn. Yeah. Yeah. So this is giving an a priori bound. So this is incredibly strong, right? In particular, this implies that every element of your group is arbitrarily badly distorted, right? So distortion was defined even for uncountable groups by Emmanuel the other day. It's saying that within some finitely generated subgroup, you can write powers of it as surprisingly short words, right? So to see how to get this from that, just take Gn to be a large power of f. So I don't know, f to some function, I don't know, take Wn squared, or take e to the Wn, or something like this. Take some horrible function, or some quickly increasing function. Okay? And if your group happens to have the strong distortion property, then these high powers of f can be written in as surprisingly short words in some finite set. So I think we've already kind of seen it hinted at that distortion of elements has dynamical implications. I'll say a little bit more of that later on. Maybe an easy one to say is that property SD, strong distortion, also implies another related property, which is easy to see kind of the dynamics of. So this is strong boundedness, okay, which one way of formulating this says if G, your group has this property, if whenever G acts on a metric space by isometries, then every orbit has finite diameter. Or equivalently to this, it's a nice exercise to see that this is equivalent. Every length function so what's that? It's a function from G to positive real numbers. It sends the identity to 0. Elements get the same length as their inverses. And you should have a triangle inequality. Every length function on your group is bounded. So we now know many examples of these groups actually that have these properties. I should remark, we've got some implications, right? This is a strict strengthening of property star. Strong distortion also implies strong boundedness. Strong boundedness does not imply property star. There's an example of Eve, actually, of a group that has this, but doesn't have that. But they're all sort of kind of similar in flavor questions you can ask of a group. Examples. So in general, the flavor of examples that satisfy these are groups that have kind of, I don't know, self-similarity on different scales, or that contain many disjoint or commuting copies of themselves. So the first example, and one of the earlier positive answers to this question, is that indeed the group of permutations of an infinite set not only has property star, but has the strong distortion property. And this is an example of Galois. Okay. Eve told me previously discussing this that this was not the earliest answer to this question. They're kind of implicit in work of Sabah in 1975-ish. Is the positive answer there do exist groups that have this property? I'm interested, because of kind of the dynamical implications of distortion in groups of transformations of homeomorphisms and diffeomorphisms, I'm interested in those kind of groups. And surprisingly, if you take the group of homeomorphisms of a sphere, it's an example of, or a theorem, sorry, I should say, of Danny Caligari and Mark Friedman, together with Yves de Cornouillet from 2006, that this group has strong distortion. Okay, this paper is called Distortion and Transformation Groups, and if you're interested in more context of why these questions are interesting, it's a great thing to look at. Maybe to give you a flavor for why these kind of things should be surprising, let's look at some non-examples. And to tell you a little bit more about what distortion might say dynamically. So let's suppose I have a compact manifold. Okay. If I look at the group of, I don't know, say C1 diffeomorphisms instead of homeomorphisms of M, this can't possibly have strong distortion. In fact, it doesn't even have this weaker, strong boundedness property. Because on here, I can define an unbounded length functioning by looking at norms of derivatives. So put some Riemannian metric on here that lets you define the idea of the norm of a derivative, take the supremum of, the expansion of a unit tangent vector. And I guess if I want it to be subadditive in the triangle inequality, I should take log. So defining this to be the length of f, that gives you an unbounded okay. So in particular, if you have an element that has exponential growth of derivatives, so what's an easy example of this? Say, I don't know, if I have a fixed point and the derivative has an eigenvalue of norm that's not 1. Okay. Well, then I get a kind of growth of this derivative, or linear growth in this length function. And this implies that F is not distorted. In any finitely generated subgroup. I think it was Gromov who maybe first suggested or publicly suggested that one should study growth of derivatives and the relationship with kind of growth in finitely generated subgroups. And I think this has been explored in several directions, but I don't think we have a completely good understanding. So this tells you maybe why you can't replace group of homeomorphisms with group of diffeomorphisms. Let me tell you why spheres are important also. So if I take a group, I don't know, if the fundamental group of your compact manifold is infinite, okay, then you can similarly define an unbounded length function that measures how far paths are stretched. So the right way to do this is lift the universal cover, take 2 points, and see how far they're stretched a point in the universal cover. Okay. So a nice, efficient way to write this down is take the length of F to be the supremum over all points x, y in the universal cover of the difference between either distance, so lift some path metric on M to the universal cover, between f of x and f of y. And here I have to fix a lift of my homeomorphism to the universal cover, but this will be independent of the lift. And I compare that to the distance between my points originally. So it's measuring kind of the amount of stretch. So this gives you an unbounded length function on, maybe I want isotopically trivial, the identity component of this group. Interestingly, if you take a manifold with finite fundamental group that's not a sphere, it appears to be an open question whether the group of homeomorphisms, the identity component of the group of homeomorphisms, has strong boundedness or strong distortion. I have no idea what to do. Well, I know what you need to prove, but I can't do it. So, you know, given that we have some kind of interesting examples from transformation groups and the relationship between distortion and the dynamics of diffeomorphism or a group of them, I think these are interesting questions to consider, particularly in the context of groups of homeomorphisms or diffeomorphisms of manifolds. Although it's completely natural to ask these about other large topological groups, and you might have some examples in mind you want to play with. So what's the theorem I'm going to talk about? Okay. This is joint work with Frédéric Leroux from, you know, just last year. And this says the following. So one is that the group of CR diffeomorphisms of Rn has strong distortion. And the group of CR diffeomorphisms of M, of manifold, so this should be either compact or homeomorphic to the interior of a compact manifold. Okay, so we know based on these examples that I can't possibly say it has strong distortion or even strong boundedness, but it does have the property star. And this is for all R, so including 0, which is the group of homeomorphisms case, except this ridiculous exception of n plus 1, or in your manifold case, I guess let's call this an n-dimensional manifold, dimension plus 1. So I should say something. Oh, sorry. I need 2 comments. One is I need to take the identity component here. Because they're examples of manifolds with whose mapping class group, so group of diffeomorphisms, say smooth diffeomorphisms mod the identity component, is not finitely generated. I think the 5 torus is an example, and that's a difficult theorem. Okay? It's easy to see that property star passes to quotients. Okay? So if I take one of these things with non-finitely generated fundamental group and I pass a non-finitely generated mapping class group, I pass to that quotient, that would be bad. So you can improve this to the whole group if you know about the mapping class group. What's going on here, this is the most annoying problem in mathematics, which is that we don't know the structure, the algebraic structure of the group of diffeomorphisms of regularity class 1 higher than the dimension of your manifold. We don't know if this is simple. We don't know if this is perfect. I think it's unknown whether this, I don't know, surjects to the real numbers. Okay, and again, if that did, that means your group doesn't even have property star. But in all other cases, it's known this group is perfect, and actually, the identity component is simple. No. So in fact, the group of compactly supported diffeomorphisms does not have this property. Take an exhaustion of Rn by compact sets. Choose one Gn with support equal to each one of these compact sets, getting larger and larger. If you have a finite set of generators for your S, then there'll be some bound on their support, and so you couldn't have possibly got your whole thing. Okay. So somehow, yeah, we're using unboundedness in a very big way. I have no idea, right? In particular, I mean, this might be true. I suspect it's not, right? I think we all suspect it's not. But if it is, then you can't possibly have property star. Yeah. Yeah. Mather's example. Yeah. It is not. But that's C1 plus bounded variation, and I don't know if we believe that's true for C2. Yeah, so, yeah. So Andres' comment is that, yeah, if you put, I don't know, 1 plus bounded variation of S2, there is such a surjection. So, sorry, of S1. 1 plus bounded variation of S1, there is such a surjection, or of R, due to Mather. So these are subtle questions. Okay. Maybe another thing to point out is that, I don't know, if you take measure-preserving diffeomorphisms of a manifold instead, so you could ask this for smaller classes, then again, this is not going to work out. So an easy example to think of is, I don't know, group of diffeomorphisms of a torus that preserves some measure. There's an average kind of rotation vector that gives you a homeomorphism to R2 mod Z2. That's surjective, and so this also won't work. Okay, so what am I going to do? I want to give you, well, I guess we're not using that board. What's my plan? Is in the remainder of the time, I'm going to give you a proof of the easiest possible example of this theorem, which is that the group of homeomorphisms of just R1, the real line, has strong distortion. So that's R equals 0, n equals 1 of the first case. And the point is that this uses a classical kind of standard trick that you all should know, and this is an easy enough example that I can kind of give the trick in a very clean setting. And after that, I'll tell you a bit about what you need to do this construction will be essentially not smooth and essentially one-dimensional, so there's a bunch of work to do here. And then realistically, I probably won't have much time to say about the manifold case, but I'll do my best if I can. Okay. And something to think about as I go along is that this is a very, I mean, essentially, there's one of these kind of nuggets in the proof here that, much like the observation of the other day that there's kind of only one trick to prove simplicity, there's kind of only one trick to sort of swindle an argument like this. This is what Galvin does in there. There is a trick that's used in basically every example, some variant of it. So as you're learning this, you should maybe try and mentally apply it to one of your favorite groups. Or we can do that in the problem session. Okay. You know, I guess my other motivation is I'm just interested in the structure of groups of homeomorphisms and diffeomorphisms generally. These are very rich groups. Their algebraic structure determines the topology. It determines even, you know, the manifold that underlies the group. And yet we don't know very much about, you know, what subgroups it has or what other properties we can find. So these are just kind of interesting probing questions. Okay. So proof that homeo-spline has strong distortion. Okay, so first observation is that strong distortion is inherited. If I can prove it for a finite index subgroup, it's pretty easy to show that then it will hold for the whole group. So I'm going to pass to the index 2 subgroup of, say, orientation preserving homeomorphisms. That'll be good enough. Okay. So I'm given some sequence of orientation preserving homeomorphisms. And what do we want? I want to define some finite set. So I'll try and insert things there. And of a fixed cardinality. Okay, so this is already fixed in size. And that generates all of these. Okay, and in fact, I'll tell you right away how big the set is going to be. I will do it with, what do we get? Oh no, I didn't look up how. Well, we'll find out in the end, but I'll tell you what the word length of Fn is going to be. There will always be at most length 14n plus 12. So in fact, it's linear. Okay, so I'm given this. My first lemma is kind of a factorization lemma and is really an undergraduate exercise once you know the statement. So given my set Fn, there exists 2 subsets of R, each homeomorphic to a union of disjoint closed intervals. Okay, so infinitely many, in both, unbounded in both directions. So that's my set. All sets of this form are homeomorphic. Such that I can write each Fn as a product of three things. Let's say Gn, Hn, Kn, where Gn is supported on X, Hn is supported on Y, and Kn has compact support. Okay, so the support is where it lives, right? It's like essentially the complement of the fixed set. So the size of the compact support will grow with n, but x and y are fixed once and for all. So I leave this mostly as an exercise, but I will give you a hint. Maybe the basic philosophy is, okay, if you had in the kind of silly extreme case, which you never expect to happen, if I had some very nice sequence that had the property that Fn of x minus x was less than, I don't know, some constant d for all n and for all x, then I don't even need the extra compact support term. Okay. Here's my line. I can take a bunch of intervals of length, I don't know, 3 times d with little gaps in between. Let's call this x. Okay. And it's easy to write down by hand a homeomorphism that agrees with F here and has support on X. Okay? And so that implies that you can compose such a thing with a homeomorphism that has support on a set that looks like this. Also a union of long intervals with little gaps. And recover F. Okay. So that's good enough to do it if you have some bound on length. You can imagine if d actually depended on x but not on n, you could do a similar thing, but the length of these intervals would have to get longer as you go out to infinity in either direction. Okay. And now, if this now also kind of depends on n, well, that's where you take things with compact support so that you only kind of have to deal with finitely many of these at a time. Okay. So the mechanism, if you sit down and write it out, is not difficult. Okay, so that's a kind of factorization onto disjoint sets. Once you've got this, that's lemma 1. Let me do a lemma 2. Let's treat so now I only have to kind of generate the sequence Gn, Hn, and Kn separately. So let's do Kn first. Okay, so I don't know, first of all, I'm going to kind of shrink things so that they all have the support inside the same compact set. Okay. So to do this, I don't know, say let big Kn be some set that contains the support of little kn, and I'll make them increasing. Okay. And let's take homeomorphism, I don't know, let's call it C for contraction, so that C of ki is contained in ki minus 1. Oop, C and subset look the same. Okay, so the net effect of this is that if I conjugate kn by Where do I need the minus sign? I want to expand and then shrink. This will now have support inside of K1. Indexing-wise, I guess I should have started with 0 so that my ends line up. Okay. So the first element of my set S will be this C. Let's keep track. And while I've got the board here, the next two I'm going to call T, S, and big A. Okay, time for a picture. Here's a real line. I've got some set K0 where everything lives. I don't know, let me give this guy a name. I'll call it little a n. And everything has support there. So I told you the next things are going to be T and S. Let's define T and S. I'll take S that displaces K0 off of itself. Okay, so here's a picture of S, the image of K0 under S. And if I iterate, I get a bunch of disjoint copies. Let's have them accumulate. And in backwards time, they'll also be disjoint. And let's take T that displaces the support of S. So if these accumulate back here, I'm going to take another homeomorphism of line that takes this interval to this disjoint one. Okay. So this is the kind of classical swindle that is used everywhere. I don't even know the first example of it because essentially the same trick appears in many forms. Okay, so maybe I'll bracket kind of where S lives, and T is now taking this disjointly over here. If I iterate, I get a bunch of disjoint copies. Okay, there's S and T, and now I'm going to define a homeomorphism that does all of these ANs at the same time. So the ANs live here. On my white set. Okay. So I'm going to define big A, which does all of them simultaneously but on displaced intervals. So I'm going to put A0 here. It's going to, A0 is going to be the restriction of A to K0, my original interval. And over on this piece here, I'm going to put also A0, but I mean, technically, I guess this is a conjugate of A0 by S. So I should do S inverse A0S. Okay, and on this little piece here, the restriction of A to this piece will be S minus 2 A0 S squared, etc. I'll put a copy of A0 on each of these intervals in forward time. Okay. And then I will look at the conjugate of this picture by T. Okay, so this is now T of my original interval, T of my second one, third, fourth. Okay. And on all of these, I'll put a copy of A1. Okay? So here's A1, except really A1 lives there. So I better, this is actually going to be a conjugate of A1 by T. And here, I want to put a copy of A1, so I should conjugate first by S and then by T. Okay. Questions? Or is this trick just very familiar? Okay. Okay, so I mean, I can actually write down a formula for A and it's awful, but now you can, if you want to recreate it yourself, it is a giant product over all, let's say J and N greater than 0 of T to the N, S to the J, A, N, S minus J, T minus N. Okay, and what is the net effect of this? I've somehow encoded in one homeomorphism infinitely many from my infinite sequence. And now I'll use a little commutator trick to get any element of my sequence that I want. Okay? So if you notice that if you take conjugate of A by S, this will shift all of these over. Okay? Particularly if I take a conjugate of A inverse by S, okay, nothing happens here. S is supported in this interval. I'll look like I have a copy of A inverse here and here and here and here and going along. Okay? So when I compose that with my original A, everything will cancel except A0 living where it used to live. So what I just said is that it's easy to check that if I compose A with a conjugate of its inverse, I get A0. And more generally, if I shift the whole picture by T first, so that, I don't know, AN is where the action is, and then take a commutator, I can recover AN. So I think AN, if I did it correctly when I checked this, let's conjugate by T first. Okay, that's the new A, and now I'll do, T n A T minus n inverse S inverse. Okay, so what is this? This is some word of length 4n plus 4 in my big set. Okay. And so my original Kn now has length in my generating set. What I have 2 extra words of length n. So it's got 6n plus 4. Happy? Good. Okay, good. This is the trick to keep in mind. If I teach you one thing today, then you can do this swindle as soon as you have a clever way of writing infinitely many kind of copies at the same time. All right, so that's the K's. Maybe I'll just, well, let's keep that. I'll make another board. And secretly, I've already told you how to deal with the other ones. Yeah. Derivatives. Yeah. This is why this trick is essentially homeo, and this is why this is infinitely easier than the other cases. Yeah. So yeah, that I will get to. Good comment. Okay. But first, quickly, I can tell you how to finish the proof of this. I already have a picture that does it for you. Okay. So here's the real line again. I'm going to try and deal with my GNs in exactly the same way. Okay, so these all have some support on some set X that looks like a union of disjoint intervals. I'm going to draw them very sparsely so that I can fit a picture in here. Okay. All right, and now I'm just going to define an S and T that replicate that picture simultaneously on each block like this. Okay, so maybe I'll define S prime, and I'll put that in my finite generating set also. That does this. This guy disjoint, that one disjoint, this one disjoint, and is supported on some little set like this. Okay. I'll define a T prime that takes the support of S in each one of these intervals, disjoint from itself, and is supported on this block. And you just insert this picture, replacing AN with GN, or with the restriction of GN to here, in each one of these blocks. Okay. So we can do it in exactly the same way. And the result is I get, in my finite generating set, what I have made a little bit bigger. This now has length. I didn't have to conjugate by anything first, so it'll have length 4n plus 4. Okay, and Fn the same way. Sorry, what did I call it? H? And that finishes the proof. Okay. Questions on what happened here? Okay, so the real problem is that, as Danny just commented, this construction is essentially non-smooth. There's a problem right off the bat, say here. Suppose A0 was, I don't know, C1, it had a derivative at this point, that derivative 2. Okay, I'm trying to define big A. It will have derivative 2 here, and here, and here, and there'll be a sequence of points with derivative 2 accumulating here, but also a sequence of points with derivative 1 accumulating there, so big A can't possibly be C1. Okay, whenever you have accumulation points like this, you're going to end up in trouble. So, problem for even diff of C1 of R is this is, to do the naive thing, derivatives will always blow up. Even worse, so there's a problem with this A right away. There's even worse when you're doing this with my sets X and Y, because not only do I have an accumulation point of little intervals here, but I have accumulation points under T that come up here. Okay? So there's kind of no hope to remedy this situation using the same kind of trick. So derivatives of big A, or even worse than the less part, in the second part, at accumulation points of intervals of support. Okay, so according to plan, what do you have to do to modify this and save the, and you know, given this, you might suspect that there's just no hope, but there is, you just have to be more clever. So here's the solution. So one thing you can do is to avoid having infinitely many copies of the same diffeomorphism or conjugates of the same one. So I want to kill this infinitely many copies of A0 accumulating in one place. Instead of taking something that looks like conjugates that accumulate, you can use a commutator trick that lets you avoid writing infinitely many copies of the same homeomorphism on disjoint intervals. So I have a minute, so let me tell you this trick. This is the other classical trick, the way to do this. And I'm just going to sketch the philosophy of it as if these were not supported in R, but diffeomorphisms of, I don't know, the plane supported in a small ball. Okay? This is essentially very similar to the argument we saw the other day. If I have a bunch of diffeomorphisms, I don't know, AN, supported in this ball, and I can write them all as commutators, I don't know, letters phi n, psi n. I can take a bunch of disjoint translates of this ball, so now my S will translate it disjointly. And I'm going to put phi 0 here, phi 1, by that I mean its conjugate by S, over here, phi 2 here, phi 3. So these are standing for conjugate by the appropriate power of S to put the support there. And I'll take also T. And I'll put my size on a bunch of disjoint balls. Okay, and now you check, oh, and let's call doing all of the phi's simultaneously big phi, and doing all of these psi's simultaneously big psi. And right now, if I take the commutator of these, all of these little components have disjoint support, and I'll get A0, the commutator of phi 0 and psi 0. And in general, if I first conjugate this by a power of S, and then conjugate this by the same power of T, and take a commutator, I'll get phi n, whatever, sorry, I'll get AN, the number that's the appropriate conjugate of this. Okay? So the point here is I didn't have to take infinitely many copies of the same diffeomorphism. I could take just one of each from my sequence. There's still a problem. First of all, you have to kind of realize this picture on the real line, not in R2. And then that's not so bad to do. But then there's kind of this technical problem where I have my sets X, which are already a union of infinitely many disjoint intervals. And I'm trying to do this, you know, on infinitely many copies of a piece of support of AN, all at the same time. Okay. So part 2 is a nasty technical lemma that says you can do this without having supports accumulate anywhere. So I'll write down the statement just to indicate, you know, what is the main trick here? We're pushing supports to infinity. So part 2, here's the trick to push to infinity. It's a lemma. And it says that there exists intervals I'm going to only take them to be in half of R, and you'll see why in the middle in a minute. I'm going to try and make things look symmetric. And S and T that are smooth diffeomorphisms, orientation preserving of the real line, such that, okay, well, according to the picture, all the images should be pairwise disjoint. So S to the I k, T to the j, I k prime. All of these are all pairwise disjoint. Okay, that's for I and j anything. And I'm going to make their forward iterates not accumulate anywhere so as to save myself from this problem. So the collection of things that look like S I of this interval and Tj of any other interval. Sorry, this could be a different k. So this is for I and j greater than 0 is locally finite. Okay, so what we're doing is we're using the fact that we have infinitely much space to move in to avoid accumulation points. And that's just a technical thing where you have to build such diffeomorphisms to do that, and such intervals. So that answers Danny's question, perhaps. Let me tell you how to do Rn, and let me tell you what happens if you can't do this trick and push things to infinity. Let's keep that picture and erase this one. So I guess essentially what is happening here is we don't have compact support and we're exploiting that terribly. Okay. Okay, for Rn, you do the whole thing. Secretly, this was just a special case. My sets x and y here were not really unions of intervals, but they were a one-dimensional annuli. They all look like a union of things of the form S0 cross interval. Okay, so you have a similar factorization. Fn equals Gn, Hn, Kn, where this lives on some set x, which looks like a union of concentric annuli. So here we are in R2. Something like this. Okay? That was just the special case in R1. And as you suspect, in order to prove something like this, you have to use some version of the annulus theorem. But we have that, so you do. Okay? And now you do the same kind of trick as this radially, or the same kind of modification in the smooth case radially. So that's not so bad. But the real problem, which as predicted I have 1 minute or less to talk about, but I can at least wave a hand in the direction. When I have a compact manifold, is this technical push everything off to infinity so it doesn't accumulate is just hopeless, right? No analog of this is true. And that's why you can't get strong distortion. Well, okay, that's why this proof fails to give you strong distortion, which we already know to be false. So it's really like a host of other tools that we use to first fragment things, write them, do this kind of trick within a compact set. So you need these to approach the identity so that the product of them all will be a diffeomorphism. This is a trick that Emmanuel knows well. And write things as a bounded number of commutators. There's kind of a whole history of the tricks and tools that go into this. So I will end with saying that the answer is just do a bunch more work. Okay, there's some hard theorems you have to quote. I'm happy to tell you the details after. Maybe I should end. I always like to end with a question. Well, so one is an exercise. If you understood these tricks, hopefully you can do this as an exercise for, say, a group of homeomorphisms of a Cantor set. I would really like to know what is the best one can do for the group of homeomorphisms of a manifold with finite fundamental group. Perhaps RP2 is a nice example to start with. And I'll end there. Thanks.